let's get on to once you actually collected light with a telescope, what do you do with it? You need some sort of detector. And that means the light has to be converted in a signal that you can measure. Now, historically, people are first looking with the naked eye. What happens there is photochemical reaction that converts that into a nerve impulse, which your brain registers. And so essentially, no matter what you do, actually, you want to convert energy of light into moving electron or current somewhere. Photography was the workhorse of astronomy for almost a century. Then we went through photoelectric devices. Now we do all manner of solid-state devices. I'll talk about some of those. And today, essentially, all astronomical detectors are applications of solid-state physics. And all of them basically operate in the same principle. You capture a photon, turn its kinetic energy into an electron that can be then accelerated by some voltage and measured. And so a lot of photons to get measurable currents, right? They're characterized by sensitivity, different wavelengths. They each have noise, and so on. And the important quantity people talk about is the quantum efficiency, which is essentially what fraction of all photons hitting your detector are producing measured signals. It could be one electron, a whole bunch, doesn't matter. The old-fashioned way of going about it, which I'll describe because it actually kind of describes the principle of it, was through photomultiplier tubes. You're probably familiar with the photoelectric effect. The simple version of it is there is a cathode, negative charge, anode, cathode's heated, there is a little cloud of electrons, photons come in, knock out the electrons, which can then be accelerated by the voltage. This is how the old-fashioned diodes work. Now, do this in multiple stages. Have a little cathode, photons come in, knock out the electrons, they're accelerated towards the first anode, gain some energy because of acceleration due to the voltage, knock out a whole bunch of electrons, and then again and again and again, and you do this several times, and you turn one incoming photon in like 1,000,000 electrons at the end. You're still having same detected quantum efficiency, right? But at least you can measure this current. And so this is how photomultipliers work. Very similar operation for the solid-state devices, except it doesn't happen in vacuum with hot electrodes and so on, but all happens inside the crystals. And different materials can be used for different wavelength regimes, and this is different types of detectors. So for silicon, typically it goes from about 1 micron through 0.3 or so, in which case it becomes opaque. Almost all of the modern detectors in visible, ultraviolet, infrared, and now actually X-rays as well, are so-called charge-coupled devices, or CCDs, or charged metal oxide semiconductor arrays. Those are the detectors that are in your webcam. Two people who invented CCDs got Nobel Prize for it a couple years ago, and well-deserved too. So those are fabricated on wafers in same machinery that makes integrated circuits. And usually there is some grid of pixels. They're connecting wires behind it. And there is some way of clocking the charge and reading it out. You first of all, you want to cover the detector with some coating so it doesn't reflect too much. Otherwise, you have a mirror, but don't get any light. Then you have to generate charges, and this is done internally, inside the crystal. I'll show you in a moment how that's done. Then somehow you have to collect the charge, move it out in a way that's controlled as where it is in focal plane, and then those are your pixels. You have to move it without really losing too much of it. It's almost impossible. And it's still a tiny amount of charge, so you have to amplify it, so there has to be a little amplifier on that device. But schematically, this is how it works. In any metal or semiconductor, right, there is a little sea of electrons that has sufficient energy in a so-called conduction band of energy, and those are the ones that can flow as current. Then there is a gap in energy, called band gap, and there's a valence band that corresponds to energies for chemical reactions, right? So what you want is the way to knock out the electron from valence band, move it up into conductivity band so it can be moved and measured. And so that band gap is of the order of electron volts typically for visible light. And there are many, many details about this, but that's the basic idea. So you could, in principle, collect charges, but how do you actually turn it into an image? Well, the way this works is you, instead of having one electrode in each pixel to read it out, you have three. And you turn one of them, the middle one positive, and the two around it negative. And so that creates a potential well that electrons will only accumulate in the middle where there is a positive charge, positive voltage. And then when you're ready to read it out, then you just shift the pattern by one and shift by another. And so you essentially clock out that whole pattern of potential wells and pick it out at the end and amplify it. That's essentially how all CCDs work. And this is a schematic diagram. So you have this blob of electrons that have been accumulated through photoelectric effect, and then just moves, and it's read out. The infrared arrays operate in a fairly similar principle, but not exactly the same. There, every pixel actually has its own little readout electrode. And those are produced in a slightly different way. But by and large, most of the operational issues are very similar. And different combinations of metals are used in order to tune this band gap, which then tells you what wavelengths you can observe. The last modern type of optical detectors is CMOS imagers, and those are also made using same VLSI technology like integrated circuits, so they can be made fairly large, and they have now replaced CCDs in most of the digital cameras. For professional scientific uses, we still use CCDs, but webcams and stuff like that is pretty much all like this. So each one of these pixels, again, has its own little amplifier and can be read out separately. And since we can, thanks to Moore's law, we can make arbitrary complex arrays of these, this is what's used today. The future is, ideally, you'd like to be able to measure energy of each individual photon that comes in, as well as where it comes in your image and at what time. Now, currently we cannot do this, but there are new generations of devices which are just beginning, which use superconductivity, and they're essentially extremely precise thermometers. Some of them operate on the principle of lifting the temperature of the substrate just above the critical, so it's no longer conducting. Others break Kuiper pairs, but they're the most sensitive devices we have, and they provide some energy resolution for each incoming photon. So that's the ideal detector. Right now, they only exist in tiny little arrays, and they have to be kept cold with liquid helium, but that's where things are going. Another type of detector which is heavily used in infrared and even microwave background measurements is so-called bolometers, which are operating a thermoelectric effect. They're thermometers that are highly sensitive to temperature. And again, you absorb a photon that changes the conductivity of this detector, and you can measure this very precisely. So. Now, an interesting trick that's been developed here by Andrew Lang, Jamie Bock, and collaborators are so-called spiderweb bolometers, which put this crystal that actually does the business in the middle of a mesh-like antenna that looks like a spider web. So that antenna can collect photons of longer wavelength normally would, and still can convey that thermal change to the tiny crystal in the middle. Caltech and JPL are actually among the leaders in the game of producing most sensitive detectors. And this is why it's people like Jamie Bock here who measure these amazing things in microwave background.